Hello everyone, welcome to our new video. This is part 3 for our linear algebra chapter. So let's continue with a few more examples. So we have seen the Gaussian elimination technique. So we have been talking about solving systems of linear equations using the Gaussian elimination method. In this example, we have a system of equations where we have two unknown variables, x and y. And on the right hand side, we have 1 and k. So this k is unknown. And in this type of example, we are supposed to analyze the solution with respect to the unknown variable k here. But we do, as usual, write down our so-called augmented matrix. A here is the matrix of coefficients in this system. So we fill these coefficients, the first coefficient in front of x, 3, and then 2, 6, and 4. So we write the first equation coefficients in the first row, the second equation coefficients in the second row, and we have the right-hand side 1 and k given in this system. And we draw this line to separate the left and right hand side of these equations from each other. And then what we do as usual is the row operations in order to get the leading term below the diagonals equal to 0. So if we multiply the first equation by 2 and subtract from the second one, so if you multiply the first equation by 2 and subtract the elements from the second row, so minus 2 times 3, but actually if we multiply with minus 2, then we are adding to the second row. So this becomes 0, and the second term also becomes 0, and this becomes k minus 2. So here, as we see, since both of these terms are 0, essentially we have here 0 times y equals to k minus 2. So if both sides are equal to 0, I mean if we have 0 equals to 0, this is always a true statement, and basically effectively we have a single equation here in this scenario, as I mentioned. And in order to have this condition, then k is going to be equal to 2. So in other words, if k is equal to 2, then we will end up with infinite solutions because we have two unknown variables, but we have only one equation. So that implies infinitely many, because two unknown variables and one equation, that's the equation of a line which implies infinitely many points that pass through this line. So that's infinitely many solutions. If that's not the case, if this is not equal to 0, but for example, if this is equal to 1, 0 is not equal to 1, so that is inconsistency, and we don't have any solution. So we say no solution in this situation. And as you see, if this is equal to 0, we have infinitely many solutions, and we effectively we have all the x and y values that satisfy this equation is one of the infinitely many solutions. Another example here. Suppose we have this system now with three unknown variables x, y, and z, and on the right hand side we have these parameters a, b, c. So we will start as usual. We will write down the coefficient matrix A, and then write down our augmented matrix as I repeat. So this is my coefficients. So 2, minus 1, 3, the first equation. Right hand side is A. So you put the right hand sides here, and then just complete writing this. Once we have written this so-called augmented matrix, we will start to do our row operations in order to get these below the diagonal terms equal to 0. Because remember, if we can get these equal to 0, the last row here will give us the solution for the last unknown variable easily, and then we can plug into the previous equations, second equation or first equation, in order to get the remaining variables. And also note that it is usually what we desire, to get this leading term equal to 1 in the Gaussian elimination method, because if I have 1 here, I can multiply the first row with 2 or 7 and just subtract from the second or third rows to get these terms equal to 0 more easily. So in order to do this algebra more easily, it's better if we have 1 here. Okay, so for example, the second row starts with 1, so we can immediately swap. We can do row, we can interchange the order of the rows. That's also allowed. So we can plug in the second row as the first row, and then the first row we can write it as the second row. So we interchange these locations, and don't forget to also change the right hand sides. So once you do that, now you can multiply the first row by, let's say, -2, and then you can add to the second row. So that gives you 0 here. This becomes 0. And then this becomes -5, 1, and a minus 2 times b. And similarly multiply the first row by -7, and then add to the third row this time. This one will cancel out. This will become 0. And then we have 4 minus 14, we have -10. And we have 9 minus 7, that's 2. And then we have c minus 7 times b. So as you see, as desired, we get these terms equal to 0 in the first stage. And then in the next step, we want to get this term also equal to 0 with similar row operations. And one of the things you can do is we can make this leading term here equals to 1 by dividing everything by -5. So if you divide everything by -5, this becomes -1/5. And here you also update. Now, you can actually, at this stage, you can multiply the second row with -2 and add to the third row. So that will also cancel this term. So if we multiply with a -2, so this will become also 0. And then we have c minus 7b minus 2a plus 4b, these terms. So as you see now, we got both of these terms equal to 0. So actually this term, if this is equal to 0, now if we get 0 equals to 0 situation, then we will say we have infinitely many solutions. But the 0 equals to 0 situation is possible if this right hand side equals to 0 as well. So if this is equal to 0, then we can easily say we have effectively less equations than the number of unknowns. So that implies we have infinitely many solutions. So it's not possible to have a unique solution in this case.